So now I'm going to go 5 or 10 minutes over time, no more, because I want to tell you the big beyond the Higgs. First of all, within the Higgs that we found, we have not clarified completely that it is the Standard Model Higgs. We have not measured completely its characteristics. We're doing this now with the full data set, and we will do it as we go in the higher energy run, which is going to be the almost 14 TeV run that will start in a year from now. We have to clarify if there is more than one Higgs and how many more. And the reason for that, I alluded when I was talking about all these flavor problems, that we might have to have an extended Higgs sector to understand all these different patterns in the masses of all the particles. And this is, in fact, one of the biggest part of the LHC challenge and program in the next run. Supersymmetry, in fact, predicts, when I talk about the extended Higgs, the richer Higgs, supersymmetry predicts 5 Higgses, that they are different in masses and other properties. Okay. Now, you might have read that Eureka, the Higgs, let's celebrate champagne and go home. No, not the way it is. We are scratching our heads completely with the mass of the Higgs we measured, because in fact, the mass of the Higgs, it's giving us a borderline disorder. The 126 Higgs mass is at the edge of the stability of the vacuum, and I will explain that in a minute. It has to do with a calculation for the vacuum of the universe based on the mass of the Higgs and the mass of the top. And the 126 is giving us a big headache if there is no other new physics. I will explain in a minute. If we start thinking about supersymmetry the way we have been thinking about it for 40 years, the 126 is giving us a very big headache. It is at the border of being acceptable for normal SUSY, which is the minimal supersymmetric standard model, MSSM. And you see the border there, and in order to accommodate it, mostly we have to make extensions of supersymmetry. So supersymmetry, the vanilla supersymmetry, is not good enough for this 126 Higgs. And if we consider other stronger dynamics and composite Higgs, it is rather too low. So it's too fat to be MSSM, it's too low to be composite. If there is no other physics, it makes a disaster for the vacuum of the universe. So this is kind of a situation where after the champagne, you have a hangover and you wake up to this problem, and you need now to go and analyze the data. Now, the question is, for the connections of the Higgs to the beyond, is it indeed true that, is it indeed the case that the Higgs destabilizes the vacuum? How does the scale, in other words, why the Higgs has the 126 GeV mass, and then the connection of the Higgs to the dark matter. Now, I think that I alluded again in the flavor problem is that we need to understand how the Higgs talks to the neutrinos, and if it is also related to inflation or dark energy. All of these connections are really open-ended. These are questions. These need a program, an experimental program, both a precision program and a discovery program. Now let me show you the stability. Let's not read the words, but let's see the plot there. This is the little part of the pant of the Higgs Mexican hat, the pant that it is on the bottom of a bottle. And as I will change it, you see that when the trough was very well lined up, but then as I change the potential, I can make it turn around, so the Mexican hat can go around. So what I thought was a stable state could actually be a state like on the bottom right plot, where I can tunnel from a false vacuum to a true vacuum because my Mexican hat potential turned around. So now In fact, the opposite can happen as well. But in this case, I'm saying that if I go from the false vacuum to a better energetically favored vacuum, the universe would bubble away and it will appear in a different vacuum. Of course, this sounds, it would be 10 to the 100 years, and this sounds like big nonsense. But in fact, if I consider no other physics, this is what I'm led to with the quantum mechanics that I know. And of course, this is something that we need to investigate. If I put supersymmetry, of course, this is in the plot that is showing here. The metastability is shown in yellow, and it is given as a function of the mass of the Higgs and the mass of the top. Of course, if I put the new symmetry, supersymmetry, and new particles, this plot on the left goes away, and I have no problem with the universe or the vacuum. I'm not going to bubble away. So I'm going to now talk, the last section is about matters, the dark matter, and how it is connected also with the Higgs. So, well, that's luminous matter. We see it from all the observations in the sky, and this is dark matter. We don't see it. It's also not exactly transparent, but if I put dark matter in front of luminous matter, I will see distortions of luminous matter as if the dark matter is a lens. Dark matter interacts gravitationally. The first dark matter, let's say, discovery, I would say, of the dark matter was by Theodor Zwicky, who was a Hungarian physicist at Caltech, and he was really nasty, and nobody liked him. And therefore, when he published the paper that in a cluster of galaxies, they were not galaxies then, they were called nebulae. In a cluster of galaxies, he calculated with a virial theorem from the gas how much mass that would have. And that's, the virial theorem is talking about potential energy and kinetic energy. And he found a factor of 500 more than the calculation with the luminous matter. So he wrote a paper, and this is the paper, and nobody believed him because he was so nasty, not because they didn't want to consider him, to consider his findings. Now, that was the dynamics of many galaxies, the clusters of galaxies. For the galaxies themselves, how galaxies are being comprised, they're being comprised by stars and gas and dust, the black hole in the middle, huge black hole in the middle, and also dark matter. And this was inferred by measurements of the stars, we call them the rotation curves of the stars in the galaxy, and the rotational curve is on the y-axis, and the r, as far as we go from the middle of the galaxy outside, is on the y-axis. And just with Newtonian mechanics, you would expect that the rotation curves would slow down as you go out of the galaxy. In fact, the data is observed to be flattening there. And so came the whole headache about what it is that the baryonic matter in the stars, in the galaxies, is scaffolding to, so that you get this stabilization there. And the thing that first people did is they assumed that the galaxies are embedded, the galaxies are flat, and they're embedded in a big dark matter halo, and we didn't know what dark matter is, but we knew that from this that it interacts gravitationally. For the astronomers, that's pretty much the end of the story, because they don't care what it is. So the discovery is done, there is dark matter, we've got it, here it is. Vera Rubin was the first one to do these rotation curves. And again, this is showing the same diagram and the Keplerian expectation. And this is showing the actual data that she measured. So there's another way that you can see it, that you can observe it in the sky, that there is dark matter. And this is with lensing. This will be explained in the last lecture a little more. But gravity, if you put a big gravity, a big mass gravity, the light from a faraway star system, galaxies and clusters of galaxies will be distorted as if you go in the distortion mirrors. So you will see in the sky images that have little lines around them of galaxies like this one. And this is a simulation of which kind of distribution the dark matter would have in order to get this type of distortions. The distortions are these little lines that you see, which are showing you that there is what we call gravitational lensing. Now, the best, how is this, why am I talking to you about the skies and dark matter and astrophysical observations? The best clue we got for what dark matter is the particle, a kind of particle like the particle that SUSY, that is the SUSY, the supersymmetric, lightest supersymmetric particle, which is a very weird thing because supersymmetry was not built in order to have this particle in. On the left here, it shows you the mass energy budget of the universe, and we are the special little tiny percentage of the two slices. One is the neutrino slice, and one is the rest of all the baryonic matter. And the rest is dark matter, 23%, and 73 dark energy, for which when you don't know what it is, don't even speak of it, but we do anyways. And look how much we speak about it. In the past 5 years, we have gotten a renaissance of theories of dark matter because we haven't found which particle it is. We have been looking for it as a particle with experiments in the sky, experiments underground, and the collider experiments, and we haven't found it yet. And so to understand which space is there still to explore, we have made tons of theories of dark matter: warm dark matter, axion dark matter, soliton dark matter, sugra, gravitino, cube balls, all sorts, sterile neutrinos, all sorts of different kinds of particles and all sorts of extensions of the Standard Model. So the dark matter interaction with matter, what we know is via gravity. And this is the famous bullet cluster. You will get a good explanation about it. But in this case, the dark matter does nothing when galaxies collide, and the normal matter, dust and gas, they scatter. Could it be, however, that dark matter interacts with normal matter with the weak interactions, for example, with the Z? It could, but we excluded it. We have experimental data that we excluded it. Could it be that it is actually interacting with normal matter through the Higgs? Yes, it could, and we haven't excluded it. And we're very close to getting there on all the experiments underground and the experiments and the collider experiments. Could it be that there is something else? Of course, always there is something else that it could be. But right now, it's the time to actually, we have cornered ourselves in a situation that we will have enough experimental data to actually speak definitively about dark matter, even better to discover it. I'm not going to go through this slide except to say that there is a miracle there. And the miracle is the coincidence. The coincidence, you can say, that the neutralino, the lightest supersymmetric particle, fits the bill to cover the dark matter of the universe, the relic abundance for the dark matter of the universe. Here is in plots the words that I told you, that we are almost there. Here, the experiments are the experiments of the future that will explore dark matter interaction with normal matter. These experiments have not been done, and these experiments up to here have been done, and this is where it would be if it was via the Higgs. So we are going down here, and we will know very soon from these experiments whether the area where the Higgs is the way the dark matter speaks to matter is, and so this is extremely important time. There are all sorts of dark matter evidences. You hear it in the news. Nothing is definitive. There are many anomalies. Nothing is definitive. And this is a totally open-ended puzzle. And I think dark matter and new physics is the biggest, absolutely the biggest problem in physics today. This is a network that represents the dark matter in the universe, and it looks like indeed the scaffolding where matter, the luminous matter, is hanging on to. It's gravitational for the moment, and we don't know anything else other than that. This is the last slide. I want to emphasize for the Higgs connection to the beyond, the major, important, big topics are the dark matter, whether the Higgs is a portal to the dark matter, is the electroweak baryogenesis, and you're going to hear a little bit about that, and the electroweak phase transition. This is the first real cosmic event in the evolution of the universe where we actually have the phase transition and we have mass endowed to the particles. And also the principle that creates and stabilizes the electroweak scale, how the Higgs talks to the neutrinos specifically with their little masses, and the dynamical origins. Do we have more Higgses? The dynamical origins of all the flavor, and the masses, the mixings, and CP violation. And of course, when we solve all of the above, extra credit comes if we figure out what is the connection of the Higgs with dark energy. Namely, this is going to be covered in the cosmology lecture about the acceleration, the expansion of the universe at an acceleration. So this needs a multi-decade global experimental effort on many fronts: particle physics, nuclear physics, astrophysics, even precision astronomy can give input, and of course cosmology. I have told you this. I have made the prediction that we will find that we can find supersymmetry at the LHC. So so far we haven't, and if we don't on the next run, you will hear me being at a pause because I think we need to have new ideas. If we don't find super partners at the next run at the energy scales that we expect them, then we're going to be looking for new ideas in this field. That's the end. Thank you.